Welcome to my last video on Poisson distribution. So in this case, we focus on non-homogeneous Poisson process. So let's define what is a non-homogeneous Poisson process. So we have a lambda t, which is the function with a domain of non-negative numbers. Also the range also is a non-negative number. And we are assuming that lambda t is a Riemann incredible function. And then the counting process NT is called the non-homogeneous Poisson process with the rate lambda t if the following conditions hold. So we already see the initial condition. So at time 0, there's no number of arrival. Also, we're assuming that we have an independent increment. So which says that, say we have this is 0, and this is s, and then suppose this point is the t plus s, and then we say that the number of arrivals, which is in this time interval from 0 to s, which is ns, also the number of arrivals in this interval starting from s, also ending at t plus s, and would be independent. And the rare event also no simultaneous arrivals still holds. So now we have three conditions that the property n of t plus delta minus nt equal to 0 is about equal to 1 minus the delta t instead of delta times delta t and then plus the little o delta t. Sorry, there's a delta t here. And the chance that n of t plus delta minus nt equal to 1 is about equal to lambda t times delta. And also the chance that n of t plus delta t minus nt larger than or equal to 2 is little o delta t. So here's the picture. So here we have this t, and this one is the t plus delta t. So the n t plus delta t minus nt is the number of arrivals in this time period. And then we talk about, the chance that this random variable can be three cases. Either there's 0 or equal to 1 or bigger than or equal to 2. And each property are given in either the first equation or second equation or third equation. So the difference between the homogeneous and also the non-homogeneous Poisson processes is whether the condition of stationary increment holds. So for the homogeneous Poisson process, we still have the stationary increment. So in that case, the lambda t is just equal to a constant. In that case, lambda t is just equal to the constant. But if this condition is not true anymore, and then we have this non-homogeneous Poisson process. The question still remains the same. So we want to derive what's the property mass function for nt for any given function lambda t, which is Riemann integrable function. So we have this theorem 4. So for a non-homogeneous Poisson process with the rate lambda t, and we claim that the n of mt plus s minus nt will follow a Poisson distribution, and with the mean value which is equal to integration of lambda u, and then starting from t and ending at t plus s. So here's the proof. So in this proof, we're still using the moment generating function. So as for large n, we partition the interval from 0 to t to n sub intervals starting from tj minus 1 to tj, and where this tj is defined to be number j and then times t over n. So we define, says, this t over n will be delta t. So we know that the nt will be equal to the sum of xj, and each xj is equal to ntj and then minus the ntj minus 1. So follow the independent increment condition, we know that these xj's are independent. But since we do not have the condition for stationary increment, so the distribution of x1, x2 up to x whatever n are not identically distributed. So now we calculate the moment generation function for each xj. So by definition, it's equal to expectation of e to the y times xj. So it's equal to this form. And we plug in this x value equal to 0 and give us this term. We plug in this x equal to 1 value and then give us this term. And then this is the remainder. And as we see before, you can see the function e to the y times x can be very large if the x value is large. So which means that we have to prove that this term, the chance that xj equal to x, must be very, very small. To achieve this, we consider the event that xj equal to x for any given value x which is larger than or equal to 2. And then we define, say, s1, s2 up to this s sub x be the x arrival times in the time interval starting from tj minus 1 and to tj. So that is, here's the tj minus 1, and this is tj. And the width is equal to delta t, which is equal to t over n. And then we have s1 here, s2 here, and da up to this s sub x here. And we claim that all of these arrival times, s1, s2 up to s sub x, are different. That is, the chance that xi equal to si plus 1 equal to 0 for any I. So now we use the method of contradiction. So assuming that this claim is not true, and then there exists the time s0, also an integer value j0 bigger than or equal to 1, so that the chance that si0 equal to si0 1 plus 1 n0 plus 1 equal to the number s0 is equal to a constant c, which is bigger than 0. So this statement just says that there are two arrival times at time s0, and let n of s0 minus denote the left limit of n of s when s increase to s0. And then we know that the chance that ns0 minus the ns0 minus bigger than or equal to 2 should be bigger than or equal to the chance that s0 si0 equal to s0 n0 plus 1 equal to s0. Also, this property, as we assume, is equal to number c, so this is equal to c and also bigger than 0. So we conclude that this property is a constant and also larger than 0. So this fact actually contradicts with the property C3, which says that the chance that n of t plus delta t minus nt larger than or equal to 2 is equal to a little o delta t. Okay, and then this one implies that the S1, S2 up to S sub S are all different. And know that the chance nt minus nt prime equal to 1, it will be less than or equal to ntj minus ntj minus 1 bigger than or equal to 1 for any tj minus 1 less than t prime and less than t also less than or equal to tj. So the picture is like this. So here's tj minus 1, and this is tj, and this is the t prime, and here's the t. So because this fact, we know that for any x is larger than or equal to 2, so the chance that xj equal to x by the previous discussion here, so we know that this is equal to the chance that n at S1 minus n at tj minus 1 equal to 1, and then ns2 minus ns1 equal to 1, up to n of s sub x minus n s sub x minus 1 equal to 1. Because this S1, S2, and S3 up to SS are all different. And also, by the independent increment, we know that the property of this sequence is equal to the product of each individual properties. And each of these property, because of this fact, so we know that each of these property will be less than or equal to each of this property will be less than or equal to this property, and then to the power of x. So it's equal to lambda of tj minus 1 times delta t and then plus little delta t. So we conclude that the chance that xj equal to x will be a very small number. So now, the moment generating function for xj is equal to this term. We already showed that. And then we use this term and then subtract this part, so which is here. So this will be less than or equal to the summation here. Also less than or equal to e to the y x and then times this to the power of x and then plus the little delta t. And we can clearly see that this one actually is the power series. So the sum of a power series is simply equal to the first term in the power series, and then over 1 minus the ratio between two consecutive terms. And because there's a delta t here, and then this one will be the little o delta t. So that is the moment generating function for xj will satisfy this equation. Okay, because the nt is equal to the sum of xj, and then the moment generation function for nt will be equal to the product of the moment generation function for each xj. So it's equal to this product. So now we can take the limit for delta t go to 0. So we have this limit. And we replace the delta t by t over n. So we have this expression also. And also due to the lemma 3, we know that this limit actually is equal to this value. So which is e to the ey minus 1, and then integration from 0 to t, and then lambda u and du. Also, the moment generation function for z, which is Poisson, and which this as the mean value, which is given by here. And because these two functions are the same, so we know that the nt, also z, will have the same moment generation function, indicating that the nt actually is a Poisson random variable. So this is what we need. Due to the independent increment condition, we know that n of ts minus plus s minus nt and also nt are independent. And also both nt plus s, also this nt, follow Poisson distributions. So their moment generation function actually satisfy this condition. So the moment generation function for nt plus s is equal to the moment generation function for nt, also the moment generation function of nt plus s minus nt. So we can compute this moment generation function by using the ratio of this one and then divided by this one. So which is equal to this. And this one is the moment generation function for new Poisson. So we know that the n of ts, t plus s, and minus nt follow the Poisson distribution, and with this value as the mean value. So this is what we claim in the theorem 4. So now let's show the lemma 3. So lemma 3 says that we have a Riemann integrable function, and we defined ti for I running from 1 to n. And the function m sub n is defined as the product of these terms. And we claim that the limit of this function is equal to e to the y minus 1, and then times the integration from 0 to t, and then lambda s and ds. So first we take the log on this function. We know that the log of mn is equal to this term. And then we simply defined, say, these terms denoted by ai. So the log of mny is equal to the sum of log of 1 plus ai. And for any real number which is bigger than -1, and we have this condition that the log of 1 plus s is less than or equal to x, and also the log of 1 plus s is larger than x minus x squared. And this inequality will allow us to estimate the log of mny, since we know that this log of mny will be less than sum of ai, also larger than the sum of ai minus ai squared. So now we derive the sum of ai as this. So can be rewrite as the e to the y minus 1 and then the sum of lambda ti times t over n and then plus the little o 1. And this term is simply the integration of lambda t over 0 and t. So we know that the sum of ai will converge to e to the y minus 1 and then integration of lambda s from 0 to t. Also, each ai is a large O 1 over n. So we know that the ai square is a large O 1 over n squared. And this will implies that the sum of ai square is a large O 1 over n will convert to 0. So if we put this together, and we know that this log of mn will be less than or equal to sum of ai, but it's larger than sum of ai minus the sum of ai squared. But again, this term actually goes to 0. And this term actually converts to this value. So we conclude that the limit of mn will be equal to the e to the y minus 1 and then times integration of lambda s starting from 0 and to t. So that's the end of proof for lemma 3. So in the videos number 2 to number 7, we have derived the property mass function for Poisson random variable in several different ways. The first is from a homogeneous Poisson process. The second one is as the limit of a sequence of binomial random variables. And also we can derive the Poisson random variable from an IID sequence of exponential random variables. And also we can derive the Poisson distribution from a non-homogeneous Poisson process. So we find out that the moment general function actually can apply to all cases, and also is accessible to undergraduate students. I need to emphasize that the linear differential equation method, also the characteristic function method, can also be applied to non-homogeneous Poisson process. But since this approach involves some differential equation knowledge, also this method involves the complex number, so these two methods may not be as easy as the moment general function method. Thank you for watching.